Hi guys, Mr. Saber here. Today we're going to be talking about finding the domain and range of functions when they are written as equations. I'm assuming by now that you know what I mean by each of these three vocabulary words, domain, range, and function. And I'm also assuming that you know how to read the different types of function notation that I will be using throughout this video. Braces, inequality signs, and also brackets and parentheses to describe an interval. So the first thing, polynomials and exponential functions have implied domains of all real numbers. When I say implied domains, that's what I'm talking about throughout this video. Implied domains means I'm talking about just what the equation says. If we're in context of a word problem, it might tell you more things like that the values have to be positive, that you can't buy a negative number of tickets, or a fractional number of textbooks, or something like that. But just for the equation has implied domains, and those will be all real numbers. Linear equations, polynomial equations, exponential functions. These all have all real numbers because you can raise a positive number to any exponent, any real exponent. You can take any real number and raise it to a positive exponent, and multiply it by something, subtract numbers, add numbers, and nothing will break. And that's all that polynomial and exponential functions have. Now, when we start restricting domains when we have radicals, fractions, rational functions, logarithms, and then some of the trig functions also have restricted domains. We're going to focus on these, and these are going to be more of a big deal when we're talking about trig. So first, radicals. How do we deal with a radical and finding the domain of it? Well, first of all, not all radical functions have restricted domains. If we have something like the cube root of x minus 2, that is fine. And remember that that's the same thing as x minus 2 to the 1/3. That's why I'm saying with rational exponents. When we have something like either of these, you can take the cube root of anything. Well, any real number, a positive real number, a negative real number. You can take the cube root of 0 and get 0, so that's fine. So if the index is odd, that being 3 is odd, then the domain is not restricted. So we would say all real numbers. If the index is even, so we start taking the square root of 2x minus 8 plus 12, then we have to set the radicand greater than or equal to 0. And hopefully you remember the radicand is the term for what's underneath the radical. So that's what we do. We take whatever's under the radical, set it greater than or equal to 0. The 12 is pretty, but it has nothing to do with the domain. So x is going to be greater than or equal to 4 is our domain for that radical function. For a rational function, we can't divide by 0, so we have to set the denominator not equal to 0. And a rational function is the same thing as a function with a negative exponent. So if I say something like this, I can rewrite it as that. And you can see there's a denominator, which must be set not equal to 0. And then we can solve to say that the domain is x not equal to negative 7. Now, if this function is named f of x, you would say the domain of f of x is not equal to negative 7. This is not the solution to the function. It's actually the only input where you can't get a solution to the function. People try to say, well, I'm doing this problem, I'm solving it. Well, this is not a solution. Let's try a different problem. If we have k of x, then what we should say is that the denominator can't be 0. So what's the denominator? It can't be 0. So x can't be 2. It also can't be negative 2. So that is the domain of this. It's all real numbers except for positive 2 and negative 2. Logarithmic functions. Now, hopefully you remember that a logarithmic function looks like this. And we can only put in numbers. This is what just log of x looks like. We can only put in numbers that are greater than 0. We can't take the logarithm of 0. We can't take the logarithm of a negative number. So we're going to have to restrict whatever the input to the logarithm is. That doesn't mean that in this function t will have to be greater than or equal to 0. It means that this is expecting that the input will have to be greater than or equal to 0. So we set 4t squared minus 9 has to be greater than or equal to 0. I don't think we spent a lot of time solving inequalities with quadratics, but it's not too different. And now when we take the square root, we have to take the positive and negative square root. So when we take the positive square root, we get t is greater than or equal to 3/2. And when we take the negative square root, t is less than negative 3/2. So we can have, on the number line, that looks like the numbers less than negative 3/2 and the numbers greater than 3/2. However, this is not going to happen most of the time. This is just because we had a quadratic in here. If we had anything in here, we're going to take that input and set it greater than, I made a mistake, greater than 0. So this should be greater than, that should be greater than, that should be greater than. These should be open circles because the input is greater than 0. If we plugged in 3/2, we'd get out 9 minus 9 and take the log of 0, which we cannot do. If there are multiple restrictions, then this is very rare. We're going to consider all of them. If we have this denominator, so that means that the denominator can't be 0. We also have a logarithm, and the input to the logarithm is going to be greater than 0. So that gives us multiple restrictions. X is greater than 3/2 or less than negative 3/2. And at the same time, we have that x can't be x can't be 5. So now on a number line that looks up, I'm going to do the sketch. It looks like this. Oops. Open circle at 3/2. And then when we hit 5, which is going to be over here, we have an open circle, and then it continues on. So this is the domain for this because we have multiple restrictions. We have one here, and we have a second restriction at that point. If we're finding range instead, the general strategy is to take the inverse relation and find the domain of the inverse relation, because really domain and range get switched when we take an inverse. However, some functions are not invertible. If we have something like, let me do a reasonable job at drawing sine. If we have sine, if we wanted to draw the inverse sine, well, inverse sine looks like this, but that doesn't give the whole picture. The whole picture is if we can keep continuing it. This is not what inverse sine looks like, but it's what the inverse relation looks like. So a general strategy to finding the range of a function is take the inverse relation and find the domain of the inverse relation. So between -1 and 1 is the same thing as between -1 and 1 in the range here. There are specific strategies for linear, quadratic, exponential, and logarithmic functions. For linear and logarithmic, that's all real numbers. The only exception is if we have a linear function that's constant. If we have a flat line, then it only has one output value. Everything else would, because it has a slope that's not 0, would have a range of all real numbers. Quadratic functions, remember that we have a vertex. So we would say all the range is all the numbers less than the vertex, less than or equal to the vertex. Or if the vertex is a minimum, the range is all the numbers greater than or equal to the vertex. Same thing with exponential functions. We have some sort of asymptote, and that is all the y values are going to be greater than or equal to that asymptote, or greater than that asymptote or less than that asymptote. Some quick examples, and then we'll be done. Find the range of the following. This is going to be all real numbers. For y equals 5, the range is just 5. For this, we have to find the vertex. So finding the x-coordinate of the vertex is -b/2a, which gives 1. And the y-coordinate is 1 minus 2 is -1. So we have a vertex of 1, -1. Based on this, we know that it's going up. So -1 is the lowest y-coordinate. Y is greater than or equal to -1 is our range for the quadratic. Here, we don't really need to worry about the exponential piece. We do need to know that it's exponential, but the important thing is that 7 shifts the typical asymptote, which would be at x equals 0, up to x equals 7. And then because this is 4 to the x minus 2, it's still increasing and above the asymptote. So that just tells us that we're comparing y to 7, and all the numbers have to be larger than 7. So y is greater than 7 is the range of this exponential function. And we also have logarithmic function. You can pretty much say that that's going to be all reals for the range, not for the domain, but for the range. A good exercise, if you want to pause the video, is to find the domain and range of the trig and inverse trig functions. It takes a little while, and you have to think about the way that the unit circle works in order to be successful at it. But if you pause, you can try these, and I will put the answers on the next slide, and that'll be it. Thank you.